The main purpose of this experiment is to compare tensile properties of given samples, namely acrylic. The device used for this experiment is known as UTS tester. UTS stands for Ultimate Tensile Strength. This is the only apparatus used for this experiment. The device I talked about, it has its own inbuilt error value, which is 20 kilonewton of force. And because most of the materials used for this experiment are brittle, safety goggles are extremely important for this experiment. This device is electromechanical and it has jaws, so if by mistake it catches hand or any other body part while setting up the apparatus, it's not gonna stop until the emergency stop button is pressed. This can be extremely dangerous and it can injure badly.
What I'm going to talk about is the theory of why you get the results that you do when you perform a tensile strength test. Basically, it comes down to the intermolecular bonds of your material. For example, when you have a product which has been cold rolled, like steel, the grain size becomes much smaller. What this does is that it makes the material more dense, and it makes it so that the molecules are close together and their bonds between them are much stronger. So the theory behind this is that as you apply mechanical force, the differing strengths of these bonds, when they rupture, that is your fracture point. But between that, the initial strain and the fracture point, you have a period of time where it can recover from the force that you put it on. That's the elastic region, where the bonds haven't been stressed beyond recovery. After you get to the yield point in your stress-strain curve, what you get is a phenomenon called plastic deformation. What that is that the bonds become adjusted and they permanently deform. It's been overstressed. They can't actually recover. So what happens there is that your molecules get forced apart, but they haven't actually broken apart. They're still connected, but it's becoming weaker and weaker and weaker. As you apply more force, then it becomes too much and your bonds break. That is tensile strength. Alright, so going over the procedure here. First, you turn on the machine and the controller. You then start up your datum program in the onboard computer there to the right. And here we start loading sample 1. In order to move the jaws and to operate the machine, you go to your datum program. You go on your main screen to click Operate and click the Jog button. That activates the 2 white buttons on the lower right portion of the machine. Then what you need to do is you need to zero the machine. You go to your Operate and you click your position equals 0 and your force equals 0. What this does is this makes it so that you can see where your machine is actually going. It sets your starting position, right? So afterwards you have to start a new template for a new test, where you click New Template tabs, and then you select your imperial and metric. We're suggested to use metric in this case. In that, there's a test called Tensile Properties of Plastics. Click Apply. Under the Sample Info tab, you put your customer name, also known as the group ID, your species ID of the name of the sample you're testing, Lexan, nylon, or acrylic. In this particular case, we're going to be testing nylon. It's currently going under its strain, but it takes a while, so that's alright. For your width and thickness area, you enter your imperial or metric dimensions and then click Apply. Click Test, and the machine proceeds to pull the sample apart, as well as measuring the amount of force that it has to apply to start moving it, and the distance in which it's moving from its zero position. When the test is finished, you remove the sample and click OK. After you finish your test, you need to generate a report. In order to do this, you go to the Reports tab and select the most numerically recent report under the Analysis tab. Ensure the break-off point of the material is at the end of the sample. return to Reports tab and click Reports button. A pop-up from Microsoft Access will appear, and then you select the most numerically recent test. Click Graph. And what this will do is it will give you a pop-up of your material's stress strain curve. Click Reports and print reports, and then repeat these steps for each sample.
In the calculation part, I am going to show you some basic feature for the percentage error that we find for the Young's modulus. But before I will show you, I am going to show you some basic feature of the load versus extension curve for the nylon. This is the point where the maximum load is applied, and it is around 2488.15 Newton, and this fracture point. As my friend had already told you that for a nylon has the maximum ductility and the minimum yield strength compared to other two. And if we find the tensile strength at that point and we divide it by the area, we can get this tensile strength, and from the Hooke's law we can find the Young's modulus just by dividing it tensile strength to the yield strength. So now for the percentage error, as we all know, the basic equation for the percentage error is experimental minus accepted divided by accepted. For the nylon, we find the experimental value for the Young's modulus is 1277, and we got this accepted value from the international peers, that is 2000, and this we divide it by the accepted value, find it 36.15%.
I'll be talking about the discussion of this experiment. When you look at acrylic, the sample almost immediately snapped when the force was applied, while when we compare it to Lexan, which stretched for a little bit before the actual fracture, and in comparison to nylon, which had the longest time, it stretched for a very long time with little force being applied in the plastic region until it sheared around the shoulders and then finally fractured. So looking at these graphs of the result, acrylic doesn't actually enter its plastic region and therefore has an almost linear line, while in comparison to Lexan, which actually does have a minimum elastic region, plastic region, and where Lexan reaches the maximum elasticity at around 5 millimeters before it enters its plastic region, and nylon, which reaches its maximum elasticity at around 10 millimeters before it enters its plastic region. The acrylic actually expanded to about 3.768 millimeters. Though no actual stretching was seen, this may have been an error in the machine itself. And Lexan expanded to 30.029 millimeters before it fractured. And nylon expanded to about 53.68 millimeters before the fracture. So when we look at the characteristics of each piece, acrylic had the highest tensile strength but was the least ductile. Lexan was fairly tough towards its tensile strength and also had a little bit of ductility, but in terms of nylon, it had the weakest tensile strength but the highest ductility. So when we look at these samples, we actually want to know how they can really be used in the real world. So when we look at acrylic, also known as plexiglass, with its good tensile strength, would be a formidable use of windshields, airplane cockpits, or lenses. Lexan, on the other hand, is polycarbonate, would have similar uses as acrylic since they're pretty similar, but more impact resistant, and they can be used such as bulletproof glass or any high tensile strength use or and minimum ductility. In terms of nylon, with its ability to stretch, and it could possibly make a good use for a fishing line. Now I'll be talking about the sources of error. Where the sources of error can occur during the loadings. Error can occur during the loading of the samples, in which the shoulders of the pieces should slightly be above the clamps, but if this is not corrected or is misplaced during the load, it can actually throw off your results. So to avoid this problem, it is recommended that the pieces are clamped from the top and then lowered down to the bottom clamp and then locked in. And when measuring the cross-sectional area of the samples, reading error can occur because of down to the thousandths, just because it does vary around the actual cross-sectional area. So it is recommended that 3 measurements are taken around the area and then using the average of them to take the data. So in order to correct the reading measurements, it's very difficult, but it is recommended that one person takes the measurements and does the measurements in a way where it's all the same for each piece and every measurement. Another source of error was in our samples. Our sample was actually bent, so you could see that it was bent before we actually entered it into the machine, and so this could have altered our ductility or our strength. Another source of error is that the surroundings of our environment was actually, the temperature was actually very high, and this could have affected our results of our samples.